Hey everyone, I'm McCabe Levingood, and this is my Lab 6 on Faraday's Law. The main goals of this lab are to collect observational data of a magnet falling through a conductive tube of aluminum foil, and then model the magnet-tube interaction computationally, and then compare the computational predictions versus the observed data. Here are some important equations we need to know. First, we have the magnetic field, and then the magnetic flux, which is basically the change in magnetic field over an area. And then we have the EMF is equivalent to the change in magnetic flux over the change in time, and the magnetic field from a solenoid. And then from the EMF, we can find the current using the EMF equals IR. Okay, so now we're getting into the experimental portion of the lab. First, I'm going to specify a few things. The system is the magnet and the aluminum foil. The surroundings is the lab room and any external magnetic or electric fields from objects like my computer. And then the initial conditions are the tube diameter is 3.5 centimeters, the tube height is 47 centimeters, the mass of the magnet is 22.7 grams, and the initial velocity of the magnet is 0. And then I also have a short little video of the magnet falling through the tube. It's cut exactly when it's at the top versus the bottom, so you can't see it falling out, but yeah. So after taking 5 of these videos, we found that in the first round, the magnet took 2 seconds to fall, and then all the other rounds, it was about 1 second. So the average time for the magnet to fall through the tube from top to bottom was 1.2 seconds. Okay, so now we're going to computationally simulate that exact same scenario that we just watched in the video. So the first step is to basically put in the dimensions of the tube, which you can see on lines 35 through 38. Now we're going to fill in properties of the magnet, like its mass and then the magnetic dipole moment. In addition, we have the creation of the cylinder, which is going to be the bar magnet, and the initial conditions of the velocity and time. In this top function of code, we're calculating the B field, and then in the bottom function, we're calculating the change in flux over the change in time. In lines 132 through 145, we're basically seeing the time that the magnet exited the tube. And then further down in the code, we are accounting for the gravitational force. And as I talked about earlier on the equation slide, I said that you could then plug in the EMF that you got from finding the change in flux over change in time. So that's kind of what we're doing here and finding the current in the ring. In this portion of the code, we are calculating the magnetic force on the magnet and then finding the F net. And then lastly, we are just updating the magnet's velocity and position, and now we're done with the code. The computational results give us this. So we have our picture of the tube, and then a little velocity versus time graph. And the time that it took for the magnet to travel through the tube is 0.33 seconds, according to this. So now we're going to compare our experimental and computational results. Obviously, they differ. For experimental, it took 1 second for the magnet to fall through the tube, but for computational, it only took 0.33 seconds. Both of them take a second or less to fall, so that's pretty good. And then the main forces at play in both of these scenarios are the magnetic force and gravitational force. And then the differences is obviously the experimental situation is exposed to unaccounted for external magnetic fields, and the magnet fell faster in the computational model. I've already talked about this a little bit, but some sources of error are outside interference from residual electric/magnetic fields from nearby equipment like my computer. There's definitely some human error in tracking the magnet's position. Air resistance is unaccounted for, and there might be some error in measuring how much aluminum foil was present on the tube, and an error in measuring the properties of the magnet. Now to wrap things up, if the resistance of the conductor were reduced to as close to zero as possible, we'd have to look to Ohm's law, which says that reducing the resistivity will increase the current, resulting in an increased upwards force, and the magnet would either have a slow descent or be pushed up away from the tube. If holes or slots were cut into the tube, the current would be disrupted and would decrease drastically. However, the force of gravity would remain the same, so the magnet would accelerate downward at a faster rate.